Hello, let's now consider maps that are both onto and one-to-one. Such maps are called correspondences. A map is a correspondence if it is both onto and one-to-one. Let's see what this means for the arrow diagram definition of a map and the set definition of a map. So let's choose a codomain with elements 1, 2, and 3, and a codomain with elements 4, 5, and 6, and we can make a pairing of, say, 1 with 6, 2 with 5, and 3 with 4. Now we'd like to see, well, we can see this is a correspondence because it's both onto, because every element in the codomain has a domain element pointing to it, and every element of the codomain only has one element pointing to it. It doesn't have more than one. Okay, so here's the set definition, and you can see that each of the codomain elements, 4, 5, and 6, both appears and appears only once, because the number of ordered pairs is the same as the number of domain elements, at least for finite sets. When there's a one-to-one correspondence between two sets, they both have the same number of elements. Okay, now let's look at a map that's not one-to-one. It's not a correspondence. Well, it can fail not being a correspondence by one of two means, either by being not one-to-one or by being not onto. Now, the codomain here has 4 elements, and the domain only has 3. So in this way, there's no way to make these maps into there's no correspondence that exists between these two sets, because I can only draw one arrow out from each of these. So I can only have 3 arrows, so I'm always going to miss at least one of the elements, so this one can't be onto. On the other hand, if we start with the set 1, 2, 3, 4, and try to make a correspondence with the set 5, 6, and 7, well, I could start off pairing 1 with 5, 2 with 6, and 3 with 7, but I have to draw an arrow from 4, and I have to choose one of 5, 6, and 7 for it to point to, and that means that, as here, at least one element is going to be have 2 arrows pointing to it, so it's not going to be one-to-one. So this shows the case when there's not a correspondence, because the codomain has less elements than the domain, and the example on the left shows a case in which there can't be a correspondence because there's too many elements in the codomain. Okay, well, this is one example of the way that correspondences compare sets. If two sets are finite, as we saw in the previous slide, and there's a correspondence between them, then the two sets have the same number of elements. On the other hand, if two sets are infinite, that is, they have an unlimited number of elements and there's a correspondence between them, then the two sets are said to have the same numerical size as sets. We can't say that they have the same number. We can use this to define what we mean by two sets having the same number of elements. For example, let's consider the infinite set of all the integers. 1, 2, 3, 4, ... and the set of all the even integers, 2, 4, 6, 7, 8, and then ... Well, I can pair each element here with the number that's twice its size. So 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times, that's not an even number. We have to make that 8. And this would have to now, well, let's erase that and come back and we'll get 8 and 10. So 2 times 4 is 8, and 5 over here is going to be 2 times 5 is 10. So you can see here that every element of the domain points to an element of the codomain. And in the codomain, all the elements here are going to have arrows pointing into them. So it's going to be onto. In addition, no element is going to have more than one arrow pointing in. So this is a one-to-one map and onto. So we say the set of integers, the set of even integers, have the same numerical size. It's what we mean by we could say this defines what we mean by saying that there are as many even integers as there are integers. So when dealing with infinite sets, this role of correspondences leads to some mysterious results.